Good morning, and today we're going to be talking about exponential and logarithmic equations. Now, this will be another pretty short video in terms of like all the theory and everything. It's very straightforward. It's just now that we know our properties are logs and the properties of exponentials, we have the keys to solve equations now where the variable is an exponent itself. Okay, so for example here. Here's a very simple one. We're going to do 2 to the x equals, let's say, 8. Now, in the previous video, I did allude to a property, which is, if a to the x equals a to the y, then x has to equal y. And this is our exponential. Oh, sorry, my cat just walked all over my notebook there. So anyways, if you want to use this property, the key here is that the bases for the exponentials have to be the same. So if you look at 2 to the x equals 8, currently they're not the same. However, we can rewrite this equation as 2 to the x equals 2 to the third. So now that we have the bases equal to each other, we're allowed to say that x will equal 3. So this is very nice and very straightforward as long as the bases are the same. So let me show you another example here. So we're going to do 5 to the 2x minus 3 equals 1. Now, once again, you got to think of a clever way on how to get these bases the same. And if you remember, we can rewrite this as 5 to the 0. Because remember, 5 to the 0 is 1 by definition. So therefore, 2x minus 3 has to equal 0. And now what we can do is just solve for x by adding 3 to both sides and then dividing both sides by 2 to give us x equals 3 over 2. Okay, like I said, very straightforward. And you can also check yourself by substituting in your solution. So if you notice here, the 2's will reduce. You're left over with 5 to the 3 minus 3, which is 5 to the 0, which we know is 1. So all that's nice and good. Okay? Now the question becomes, what if you can't do that? In other words, let's look at this example. 3 to the x plus 2 equals 7. Now, on the left-hand side, you have an exponential with a base of 3. And on the right-hand side, you have an exponential with a base of 7. This is 7 to the first. Remember, you can still write it as an exponential, okay? But here's the problem. There is no way that we can write 7 as 3 raised to some exponent. So what we need to do is figure out an interesting way to actually solve this problem. And the answer to that question is logs. Okay, logs will allow us to solve this problem. So there's going to be a couple key steps that we want to do. So I'm going to write them down first. All right. So to solve exponential equations. All right. First thing you want to do is isolate the exponential expression. All right, now for us, that's already done. The exponential expression is 3 to the x plus 2. So that's already done. Step 2. Take the log, and I'll put this in brackets, or the natural log. You could do either or. It both work. So take the log or the ln of each side. And then step 3, solve for the variable. All right, so here are our steps right here. We're always going to do these. So I'm just going to rewrite our problem, and I'm going to do exactly what this told me to do. So we have 3 to the x plus 2 equals 7. All right. So now, step 1, isolate the exponential. Already done. Step 2, we're going to take the log of both sides. Okay. Now, if you remember from the properties of logs, more specifically, my favorite property, property number 3, if you have an exponent and you take the log of both sides, you can pull this exponent out front. That's exactly what that is saying on the right-hand side. So that's exactly what we are going to do here. By taking the log of both sides, what we can do is take this exponent, that is x plus 2, and we're going to write it out front using our log, or our exponent log rule. So from here, I can divide both sides by the log of 3. That gives me x plus 2 equals the log of 7 over the log of 3. And then finally subtract 2 from both sides to give me x equals the log of 7 over the log of 3 minus 2. Okay? And yes, this is the answer to this problem. Okay? Only use decimal answers when asked. Okay? So if the problem just says solve, we want the exact answer. This is an exact answer. If they want a decimal, the problem will say, give me a decimal answer, round it to 3 decimal places or 5 decimal places or something like that. Okay? Now, we're going to do another example here. Okay? And this one's a little bit more straightforward. So we have 8 e to the 2x equals 20, and we want to solve for x. All right, so first thing I'm going to do here is I'm going to divide both sides by 8. This is going to give me e to the 2x equals 20 over 8, and 20 over 8 reduces down into 5 over 2. Now from here, since I have an e, I'm going to go ahead and just take the ln of both sides. Now I could pull the exponent out front. By definition, the ln of e is equal to 1. So this just turns out to be 2x equals the ln of 5 over 2. And then I will divide both sides by 2 to give me x equals the natural log of 5 over 2, all divided by 2. Okay? So let's try another one here. How about e to the 2x minus e to the x minus 6 equals 0? Now, this kind of looks like something that you're familiar with. At least, you should be able to recognize what this is. First, on the left-hand side, that's a trinomial, okay? And we know when we have trinomials equal to 0, we always solve them as this. Ax squared plus bx plus c. In other words, this is a quadratic equation. It's a trinomial, so it's quadratic. And there are a lot of ways that we would go about solving this. We could factor. We could complete the square. We can use the quadratic formula. I mean, there's all these different ways that we can do this. So if you look at our problem, e to the 2x minus e to the x minus 6, it kind of has that feel to it. But the problem is right here, and I'm going to show you. We are looking for x to the second, and what we have is e to the 2x. Now, I know this kind of looks like a problem, But if you really know your rules for exponents, it's actually not a problem at all. Because remember, there was one rule of exponent, it was called the power rule. And what the power rule said was, if you have an exponent raised to an exponent, you could just rewrite it as multiplying the exponents together. So if you look at what I have, e to the 2x, I'm going to rewrite that as e to the x, all raised to the second power. So now I definitely have my quadratic equation staring me in the face. It's just this right here and this right here would be comparable to the x and the x in each one of those terms in the quadratic and the linear term respectively. So what I can do here is I can go ahead and factor this. So I'm just going to write out my factoring here. E to the x, put a minus and a plus, and this will factor down into e to the x minus 3 and e to the x plus 2. So now I'm going to go ahead and set each one of these equal to 0. And I'm going to go ahead and solve. So I'll solve the first one by adding 3. And then the second, I will subtract 2 from both sides, and this gives me e to the x equals negative 2. Now, before we move any further, we have to use a little bit of our intuition here. Remember, e to the x looks like this when you graph it, all right? Most importantly, there is a horizontal asymptote at this y equals 0. Now, the reason why I'm telling you this is because if you look on the right-hand side, e to the x equals negative 2, e to the x's are never negative because they never go below the y-axis. So we would consider this an extraneous solution. Okay? And what we would do is just go ahead and then solve e to the x equals 3. So to solve this, once again, we're going to take the ln of both sides. We could pull the x out front to give me x times the ln of e. Sorry, that looks bad. There we go. Equals the ln of 3. By definition, the ln of e is 1. So this is just x equals the natural log of 3. And that would be the only solution for this equation. Okay? So, like I said, you got to be careful when you think about this. Let me zoom out here so we can see this problem all over again. Because the first two examples are very straightforward. It was nothing more than just isolating the exponential term and then applying your rule of logs. Even the previous one here was isolating the exponential term, taking a log of both sides, and then go ahead and solving. However, with this problem here, you really had to slow yourself down. So what I'm asking for you to do every single time you do these problems is just to slow yourself down a little bit. And after every move, just kind of sit there and ask yourself, okay, mathematically, the move I just made, is it correct? And then number 2, does it make sense? All right. And if it doesn't make sense, all you have to do is email me and let me know. And I'll work through it. So, there are some of us that I've written up like 4 or 5 pages of an explanation to really try to drive home what I'm trying to teach. And I don't mind doing that. I just need to know, that's all. So let's try one more. We'll try one more. So let's go ahead, let's solve 3x e to the x plus x squared e to the x equals 0. Sorry, I just had to sneeze off camera. Okay, so first things first, we know we're solving for x. And if we look at this example here, there's a couple of things happening, all right? First, we got it set equal to 0, all right? That's a biggie. Second, I see this x squared term. Anytime I see an x squared, I'm thinking, maybe I have to factor, All right? Because remember, factoring is pretty easy. It's pretty straightforward. All right? Third, each term not only has an e to the x, but it also has at least an x. So this idea of factoring, I'm definitely going to have to do it. So let's go ahead and I'm going to factor a specific way. It may look a little weird, but if you really think about it, it's nothing new. It's just we never really wrote it like this. Because we were only factoring one thing. So here's what I'm going to do. Watch. I'm just going to rewrite the problem. And what I'm going to do is this. I'm going to factor out at least 1x, and I'm going to put it out front. And then I'm also going to factor out the e to the x, except I'm going to write it on the right-hand side. So that's going to leave me with 3 plus x inside of the parentheses. Okay? Now, the reason why I did this is just so I can separate the x and the e to the x, because I know once I factor something, I can always rely on the zero product property. And you know what this is. This is that, if a times b equals 0, then a equals 0 or b equals 0. Okay, we used it up here. We used it right here. That's that zero product property. You've been using it since intermediate algebra. All right? So what I know is this. I can take each one of these factors. So here's my first factor. Here's my second factor. Here's my third factor. And I can set each one of these equal to 0. Now, going from left to right, I'm going to solve each one of these, okay? First, x equals 0. Great. We're good there. Second, subtract 3 from both sides. I get x equals -3. Perfect. Now, it's this last one that we actually we need to think about this just a little bit, okay? Remember, e to the x, when you graph it, looks like this. It has a domain of -infinity to infinity, and it has a range of 0 to infinity, but we do not include 0 because we have that horizontal asymptote there. So e to the x will never ever equal 0. So your only two solutions for this problem are x equals 0 and x equals -3. Okay? Once again, intuition has to kick in. You have to understand what these graphs look like for the exponential, or in the next part, we gotta understand what the graphs look like for the natural log or the log just in general. So let's go ahead and let's look at some examples with equations using logs. So just like the exponentials where you have a to the x equals a to the y, then x equals y, well, you have another property for logs. So we're going to go ahead and we're going to define this first, because this is going to help us out tremendously when it comes to solving. Let me write this word better. There we go. So if log base a of x equals log base a of y, then we say x equals y. The key here is the bases for the logs have to be the same. If they're not the same, you cannot apply this. If they are the same, then you go ahead and you can apply it. So we'll start off with an easy example here. All right. The ln of x equals, we'll say 5. All right. Well, oops, sorry. That's a different example for a little bit later. Let's do this one. We're going to do log of x squared plus 1 equals the log of x minus 2 plus the log of x plus 3. So sorry about that. That second problem we're going to do in a second. So with this, the first thing you want to do before you start moving things around and everything, look at all the logs and their bases respectively. For each one of these, they're all log base 10, which is perfect, because now what we can do is we can apply this property above. The thing is, you got to make sure that you have exactly one log on the left and exactly 1 log on the right. And we don't have that yet. On the left-hand side, we're good. We have exactly 1 log on the left-hand side. But on the right-hand side, what we're going to have to do is use our properties of logs to rewrite this as the log of x minus 2 times the quantity x plus 3. Okay? Now, if you look on the left, we have a log. On the right, we have a log. So we can apply the property we just learned. So x squared plus 1 has to equal the quantity x minus 2 times the quantity x plus 3. And from here, we can go ahead and we can solve this. All right? So, excuse me, on the right-hand side, x minus 2 times the quantity x minus 3 is going to be x squared plus x minus 6 after you distribute and expand. Then we're going to just subtract x squared from both sides. That gives us 1 equals x minus 6. Subtract 1 from both sides. Oh, sorry, don't want to do that. From here, we're going to add 6 to both sides to give us x equals 7. So, like I said, very simple, straightforward, okay? And this was really nice because we had all the same logs with the same base on both sides of our equation. It's just before we could actually apply this brand new property above at the top of your screen, you got to make sure that you have 1 log on the left and 1 log on the right. So if you need to, you may have to condense using those properties that we learned back in like section 2 or 3. I can't remember exactly which section. However, that's not always the case. So let's look at this example here. We're gonna solve for x. The natural log of x equals 8. Now, with this problem, notice we have an ln on the left, but there is no ln on the right. Now, if your first gut instinct is to go say, well, why don't we just take the ln? You got to remember, you got to do it to both sides of the equation. So if you want to take the ln of 8, you're going to have to take the natural log of x. And that doesn't help us out at all. So we need some guidelines to help us with this. And the guidelines I'm going to give you are very similar to the previous. So first, we're going to isolate the log. Second, we're going to write the equation in exponential form. And then third, we solve for the variable. Okay? So if you look at our example here, the natural log of x equals 8. Step 1, the log already isolated. All right? Step 2, we're going to write the exponential form. Now you got to remember, log base a of x equals y if and only if a to the y equals x. So what we're going to do is we're going to say x equals e to the 8th. And congrats, you just solved it. Now, if they wanted a decimal approximation, give me a second, let me use my calculator here. E to the 8th is like 2,981. All right. So you could totally write out decimal approximations. This, I rounded to the nearest whole number. All right. But if you wanted, if you wanted more decimal places, you could. All right. Now, sometimes with this next example here, we need to be a little bit more careful about how we write things. All right. So here we have the log base 2 of 25 minus x equals 3. Okay. So once again, isolate the log. It's already isolated. Now, I'm going to write out what's really happening here. All right. We are going to exponentiate both sides. Let me write that out here. We're going to exponentiate both sides by 2. And the reason why I chose 2 is because that's my base. So let me show you what I'm writing. 2 to the log base 2 of 25 minus x equals 2 to the third. Okay? Now, by definition, and let me try to find those properties here real quick. So I think they're back here in section 3. Or maybe it's, where are all those properties? Here it is right here. Property number 4. So let me just erase this. There we go. So if we look at property number 4, I want you to notice something. When the base of the exponential is the same as the logarithmic in the exponent of the base, it simplifies down into whatever the argument of the log is. So if we go back and we look at our example here, that's exactly what I'm going to do here. By me exponentiating both sides by the number 2, my base and my base of the log now match, which means the left-hand side reduces down into 25 minus x, where the right-hand side turns out to be an 8. Okay? Now from here, I'm going to go ahead and just subtract 25 from both sides to give me negative x equals negative 17, which means x equals positive 17, because you divide both sides by negative 1. So the key here is to understand what we just did. In fact, in the previous example, ln of x equals 8, I did the same exact thing. It's just I didn't show it because this was really easy to rewrite in exponential form. However, you got to remember that the natural log is log base e. And by me raising both sides to the power, the e base, or exponentiating both sides by e, notice that the e's match. So you're left over with x equals e to the 8th once you simplify using property 4 back from section 3. Let me go back to that section real quick. So it's these basic ways to simplify logs that kick in. That's what makes this chapter so hard, is the fact that we are learning all these brand new properties for functions that we never really studied before, like exponentials and logarithms. Okay? So now that we kind of have an idea of that, we're going to do just a couple more problems here, and then we can call it a day. So here's another example. Let's solve the log of x plus 2 plus the log of x minus 1 equals 1. Now, hopefully, a couple of things are kind of snapping off in your brain, like little fireworks. First, notice that the bases are the same. They're both log base 10. I'll zoom in so you can see that 10 again, even though I didn't write it that night. There we go. Okay? So that's the first thing I noticed. They're both base 10, so I know somewhere along I'm going to have to take 10 and raise this equation to both sides of that. Second, I see a plus sign here, and I have 2 different arguments. So I can condense these down into one log. So I'll just keep it in red. Log base 10 of the quantity x plus 2 times the quantity x minus 1 has to equal 1. From here, I'm going to take my base 10 and rewrite this as an exponential on the left and on the right. So, by definition, property 4, since these match, I'm left over with the quantity x plus 2 times the quantity, oh, I copied this down wrong. It's supposed to be x minus 1. X plus 2 times x minus 1 equals 10, because 10 to the first is 10. Now, I'm going to go ahead and solve. This, I know, turns out to be a trinomial. When I go ahead and expand it. So let's see here. You're going to get x squared plus x minus 2 equals 10. Subtract 10 from both sides to give me x squared plus x minus 12 equals 0. Now, if you're wondering, well, how did I know to subtract 10 from both sides? It's this quadratic term. As soon as I see a quadratic term, I know that is the leading term. Therefore, that is going to dictate how I approach this how I approach this problem to solve. So here I'm going to factor x and x, plus and a minus. How about a 4 and a 3? Zero product property. X equals negative 4, x equals positive 3. And the one thing you always have to do with logs is check solutions. All right, we got to check solutions. And the reason for that, by definition, the log looks like this graphically. And you got to remember, there is a vertical asymptote here at x equals 0. And our domain is 0 to infinity, and the range is negative infinity to infinity. The problem here is the domain is restricted. You're only allowed to have positive values of x. So we need to go ahead and check our solutions. Just because we get x, x equals negative 4, don't automatically cross that out. You have to go back into the original problem, substitute it in, and then check it. All right, so we're going to let x equal negative 4, so we get negative 4 plus 2, plus the log of negative 4 minus 1. And obviously here, we're going to get the log of negative 2, plus the log of negative 5, which we cannot have negatives for logs. So we know x equals negative 4 is not a solution. And then if we want to check 3, we're going to get the log of 3 plus 2, plus the log of 3 minus 1, which is going to be the log of 5, plus the log of 3 minus 1 is 2. And then from here we can see, all right, they're positive. This actually just turns out to be 10, because remember, you're adding, which means you're multiplying those. Equals 1, and then once we raise both sides to the 10, we actually get the correct answer here. And if you think about it, the log of 10 is equal to 1. So we are good here. So like I said, you just want to be careful when you're solving these problems, okay? Because all those properties, they all pop up, they all creep in, and you just want to make sure that, number one, am I doing it correctly? Which is easier said than done, obviously. And then number two, the steps that I made, are they valid? And the only way that you're going to know if they're valid is by following your properties. And that's what, like I said, that's what makes this tough, is you got to learn all those new properties. Okay? So I hope this helped. In the next video, we are going to be doing nothing but word problems. And it is, in my opinion, awesome because they're so much fun, because they're real problems that we're worried about. All right? So I'll see you in the next one. Good luck. Have a good week. See ya.